Today we're gonna move into section 16.3 and we're gonna study the fundamental theorem for line integral. The line integral. Where here come the vector field F. And here come C here. C is a quarter of a circle. Psi t, psi t, 0 less than equal t, less than equal to pi of 2. Oh man, that looks like A. Okay. B. C is the line segment. One minus t, t. C is the vector field F conservative. If so, find a scalar function F. And evaluate FB minus FA. Where A is the point 1, 0 and B is the point 0, 1. Okay, gonna do these three problems first before we take a look at the theorem, because the problem is gonna lead us to the theorem. Okay, so first one is let's draw the curve C here. Go from here to here. Right? So at t equal to 0, you get a 1, 0, and then the other one is going to be 0, 1. Okay, so here come the arrow. C. Okay. Well, let's do f dot dr here. Everybody know when we do f dot dr, right? We are computing the work. So work is integral C f dot dr. And parameterize C. Okay. Integral 0 to pi over 2. Right? X is cosine t, y sine t. So and then dot the derivative of this one is going to be r prime t. So derivative of cosine negative psi, derivative of sine cosine dt. Okay. 0 to pi over 2. Right? Lúc nào have a negative cosine t sin t, negative cosine t sin t, so negative 2 cosine t sin t, or you can do a sin t cosine t, it doesn't matter. Okay, I'm gonna do this using a use up here. Sine square t over 2, and then multiply to the negative 2 here, 0 to pi over 2. Okay, what do we have here? We have a sine of pi over 2 is going to be a negative, right? And then 1 square minus 0 square, so it's negative 1. Okay. So that's A. Let's take a look at B here. There's going to be a line segment. 1 minus tt, 0 less than equal t less than or equal to not pi 2 though, 1, because the line segment is 1. Okay, let's take a look at B. Okay, so for B, one. Well, if you plug in t equal to 0, you get a 1 0, and then for 1 0 1, so it's this line segment right here. Oh. There's the curve C. Okay, let's take a look at it. Work is f dot dr. And then do the same thing too. Just be careful with the substitution here, right? And it's going to be a x is 1 minus t and then negative y. So it's negative t. Parameterize C. Okay. Dot dt. Now do we have a negative of 1 minus t and negative 1 minus t dt. Okay. Oh, just negative 1, huh? Well, it's just negative 1. Set myself some space here. Okay, so from A and B, hopefully you see something, right? Well, it looked like that it doesn't matter how we go from one point to another point, right? Because we can travel using the part of the circle, or we just do the straight line. Work is the same, and then there's a reason why it is the same. The reason is in C. Well, we just have to check the vector field. So that's why I say is the vector field conservative? All we have to do is just check on the partial derivative with respect to y of the first component x. Is this equal to partial derivative with respect to x of the second component? 0 equal to 0. So yes, f is conservative. But if f is conservative, then f is equal to fx, fy. It's the gradient vector of some scalar function f. From here, we can use integration to figure out what f is. Okay. Now, we have fx equal to x, integrate both sides. With respect to x. fxy x squared over 2 plus the constant c here, right? It's not a constant because when we integrate with respect to x, we treat y as the constant. So this is the gy. Again, the constant term is gy. Because we treat y as a constant. Okay. We have this, right? We're going to use the information on fy. Okay. Well, fy is the partial derivative with respect to y plus gy g prime y equal to negative y, and then you just got to do integrate both sides with respect to y. Okay. G prime y dy integral negative y dy. So that means gy is gonna be negative y squared over 2 plus c. You can either have the plus c or you can get rid of it because it doesn't matter. It's gonna get canceled out anyway. x squared over 2 minus y squared over 2 plus c fb minus fa. Oh, not this f though, because this is the point here. FB minus FA here. F alpha, what is B here? 0, 1. F of 1, 0. Okay, so f of 0, 1, well, is the 0 minus 1 over 2 plus c. I'm going to do the plus c, so you see that it is not necessary to have the plus c in here. And we see that, well, we have negative 1. Okay. So putting all of this together, what the heck is FB and FA? Okay, I'm gonna move up here, right? So we did this problem here. And when we did the part A, we figure out that the work is -1. Right? We go from an initial point to the end point. Right? Initial point is 1, 0. The end point is 0, 1. Yeah, so that's what we figure out, -1. And then, well, we compute the work through a straight line. Instead of the curve C here is through a straight line. Well, we get the same answer. So there must be something about the vector field F here. And in C, when we use the Clairaut theorem, right, we see that, oh yeah, the function in the vector field F is conservative. And so it is the gradient vector of some scalar function F. Use integration and partial derivative, we figure out the function f x, y. And then from there, we see that if we evaluate the function, the scalar function at the end point minus the scalar function at the initial point, we get the same number, we get -1. Putting ABC together, what we have is the fundamental theorem for line integral. Is the gradient vector of some scalar function, if and only if the line integral is exactly the evaluation at point B minus the evaluation at point A. Right? Where A is the initial point and B is the terminal point for any curve C. F is the sometimes call it the potential function. Okay. Well, if you want to run through the proof of this if and only effect, you got to go all the way. Line integral f dot dr. Okay. Curve C, then gradient vector. So this is going to be a partial f with respect to x, partial f with respect to y, partial f with respect to z. And then on the other side is, well, it's the tangent vector, right? Dx over dt, dy over dt, dz over dt. Yeah. Yeah. Work out the product rule. Partial f with respect to x, dx over dt. Hopefully you see this as something that we have seen before. Dy over dt dz over dt. Okay. Oh, what exactly is this one? Partial f and then dx over dt. Yeah. This is exactly the chain rule. So if it is the chain rule, then we can see that, oh, we just have to differentiate with respect to t. Huh? Of some scalar function, and that scalar function is fxt, yt, zt, and the dt here. Okay, so look at this thing here, fxt, yt, zt, right? Well, we can, it is exactly f of rt because we do parameterize this thing here. So c d over dt f of rt. Okay, everything right there. Just have to use one more thing, integration of derivative. Wow, you got to use the fundamental theorem of calculus, and then we get what we want. So the last part is going to be the fundamental theorem of calculus. Integration and the antiderivative, they're going to cancel each other out. And then in order to evaluate just f or b minus F or A. If you do this one, when you parameterize this thing right here, I'm gonna write here, parameterize C. Then here, you can change this thing into A to B. Make life a little easier to see. Conclude the proof here. Okay. Question. What does the theorem here tell us? That it tells us that if F is the vector field and it is conservative, then line integral is independent of path. Fundamental theorem for line integral tell us that for a conservative vector field, the line integral is independent of path. Or the work done moving a particle along a curve C is independent of path. It doesn't matter what path you take, answer is going to be the same. Work done by a force field is what it is, man. Line integral over curve C1 F dr is the same as the fundamental theorem for line integral. Also tell us that the line integral or the work done by a force field in moving particle along a curve C is 0 if that curve is closed. If it's closed, so here come and then make sure that this force field is the for a conservative vector field. It has to be a conservative vector field. Okay. So here come. So that is the when you do the integration, right, over the curve C, and that curve C is this, the arrow here, it's closed, right? F dot dr, then this will just be 0. When you have an integral that has this notation here, let's call it a circulation.